First of all, thanks so much for having me. I just wanted to introduce myself. My name is Sanjay. I work at a company called Akasa, where I'm the director of engineering, and I've been here basically since the company started up about 4 years ago. I'm a career healthcare technology person, so I love working on software to try to make healthcare in this country at least just a little bit better, and that's what I've spent my entire career on. And I live in San Francisco, and I really apologize that due to getting ill last second, I wasn't able to travel in person for the conference. But I hope you enjoy the talk, and if you do have questions along the way, I can't see each of you very well, but if you have a way to flag me down, feel free. Otherwise, I'm happy to stay on afterwards and talk and take questions as well. Okay, just to motivate basically what this company does very, very briefly. Healthcare administration in the United States is incredibly expensive, and that cost gets passed down to the patient. So there's a stat here that says that the #1 cause of personal bankruptcy in the United States is due to unexpected medical bills, which is really sad, and it's something we're trying to fix. And additionally, over 25% of annual healthcare spending, which is over $250 billion a year, is considered wasteful administrative work. And our goal at Akasa is basically to automate all of this and to take some of the paperwork out of healthcare and make it so that computers can do the boring stuff and humans who work at hospitals can actually focus on patient care. That's what we're trying to achieve. Oops. Okay. Now switching more into a technical gear, what does Akasa actually do? So we use machine learning to automate tasks that cannot be done via APIs. And we build a platform that's generic to any industry, but right now we focus on healthcare because there's just an enormous amount of manual, repetitive human work that's being done in healthcare every day. And one of our core value propositions is, and I'll talk about this a little bit more, is basically that we can build an API for any manual task by using the graphical user interface of the software system that's being used. So if you've heard of robotic process automation, what this means is if we're dealing with software systems that people are doing manual work in and don't have good API support, we can build computer programs that you call it as if it's an API, but actually our program is spinning up a virtual machine, actually logging into the GUI of the software system and using computer vision and controlling the keyboard and mouse to be able to navigate around the screen, do data entry, scrape data from the screen, do web scraping, and so on. So that's kind of the idea, is that we can do automations in a lot of these systems that previously were only open to manual work. And so some examples of that in healthcare are every hospital uses a desktop app called an electronic health record system. These are typically decades-old applications that have very, very limited API support. And so the vast majority of work is done over the GUI. And so every hospital employs like an army of humans to be doing all of this manual work. And that's something that we can automate. And similarly, health insurance companies have websites that you can use to answer questions like what's the status of my claim, or to submit an appeal, or do things like that. But they also don't have very good API support, and so we can build web scrapers to automate some of those common flows. I'm not going to pause a lot for questions just because I can't see you all, but if you do have any questions, again, just flag me down and interrupt me. Okay, getting a little bit more detailed, Our automations include basically two types of automation, what I call workflow automation and information extraction. So the first is workflow automation, and what that means is we are mimicking, a sequence of clicks and data scrapes and data entry that a human would normally have to do. So for example, navigate to a claim in the electronic health record system, scrape all that claim info from the system, and then go open up a web browser and type that info into the health insurance company website and click, where's my claim? Read the website response and understand what it says. And then based on what it says, go back to your desktop application and update the state of the claim in the electronic health record system. So basically, we're trying to sync the state of this data between two parties that aren't communicating very well. And we also have, I would say, some more traditional machine learning tasks, like information extraction tasks. So for example, you go to the doctor's office and they ask for your insurance card and they scan it into the system. That gives them a JPEG or a PNG, something that's not structured data. And we can run our OCR algorithms, for example, to pull out all the structured data from insurance cards or from health insurance company web pages and so on. And really all I wanted to show on this slide, we don't have to get into the details, is that some of these hospital workflows can be really dynamic and complex. Actually, what I'm showing here is a simple one, just because it fits on the slide. But we often build workflows for hospitals that have hundreds of branching points. They have looping, you need conditional logic. Sometimes you don't know which path you have to take until you get halfway through the search graph and see the intermediate results. And so this is starting to motivate why we were thinking about a workflow engine, is that we need to express these arbitrarily complex workflows, and they're not easily expressed as like a DAG up front that you can just go and execute. And sometimes the search graph is much more complicated than that. So digging a little deeper into what Akasa does, because this may help motivate the workflow engine even more. We fundamentally believe that human support is critical for automation challenges. So automation is always going to hit edge cases. You see this in the self-driving car world as well, which is what I'm showing on the right side. And we believe that robots work best when they can seamlessly collaborate with humans. And that was a core principle when we built our platform, was this idea of human-in-the-loop automation. And what that means is that at any time, if a bot has low confidence, it can call for help and instantly be taken over by a human on our ops team. Now, we aren't driving cars. We are, doing automation for healthcare. And what that means is sometimes this human takeover can be a little bit higher latency. And that ends up being something that kind of motivates, or that I'll talk about further, that motivates some concepts in our workflow engine. The other idea is this idea of customization by using standard building blocks. So we have a bunch of standard building blocks or API calls. For example, to scrape websites or scrape information off of a screen, enter data into a hospital electronic health record system, and so on. You can think of these as API calls in our library that we can leverage. But every single hospital wants a customized workflow. There's a saying in healthcare that if you've seen one hospital, you've seen one hospital. Like nothing generalizes, and so we need to provide customization by stitching together all of these building blocks in different and unique ways for every customer. And what that means is that in the limit, Akasa might have to write thousands of workflows because, again, every hospital is unique. And as such, we wanted to optimize for making the workflows extremely easy to write. So we wanted to give people like a single Python script that actually feels like Python, should be able to do conditionals and looping and and higher order logic. And we didn't want to make people write YAML or something like that because we're going to be writing these workflows over and over and over again, and just wanted to make it as quick as possible. So that was a motivating factor. And then the final motivating factor here is that sometimes our API calls have a lot of latency involved. So most of our API calls wrap operations that are happening in external systems, like electronic health record system. And some of these operations can take minutes to execute. Or let's say we call for help from a human and it's outside of business hours, so our ops team is not readily available. Sometimes it can take 30 minutes or an hour to get someone online to go help the bot. And it's inefficient for the client process to just block while waiting for these calls to return, because it could go do something else that's useful during that time. And so we needed our calls to be async, but we didn't want to make the workflows really complicated to write and have people thinking about async logic. The other thing that's important for us is that if an automation fails partway through the workflow, we actually don't want to just restart it from the beginning. Restarting is not only inefficient, but it's also dangerous because we are mutating data in external systems that we don't control. So for example, if there's a 10-step workflow and we fail at step 5, it's not actually safe to redo steps 1 through 4, because maybe we submitted an appeal on behalf of the hospital or did something like that. So the question here is, how do we get async execution, retries, and resuming while still preserving the expressive syntax of Python and making our workflows extremely easy to write? Okay, and that takes me into sort of the first technical chapter of this talk, which is going to be talking about idempotent APIs. I apologize. I actually need 1 second because it looks like my company's software update is trying to update Microsoft Teams right now, which is very poorly timed. Let's see. If I drop off this call and hop back on right now, will that mess things up?
We don't really know, but we can try.
Okay, let's give it a try. I'm sorry about that. It looks like I can't override this. I'll be back in 30 seconds.
Sounds good.
Okay.
Also, as a separate announcement, if you're getting lunch, you can come back and eat it in here. So, yeah. Really didn't like people just being on the hallways, just eating on the floor.
All right. Are we back?
Yeah. There's 2 of you, but
oh, there's 2 of me?
yeah, the other one wrote. Let's see.
Huh.
All right, we're good. We're good to go.
Okay. OK, great. Sorry about that. OK, here we go. So I wanted to introduce this concept of idempotency, which many of you may be familiar with. An idempotent operation is one that can be applied multiple times without changing the result beyond the initial application, right? So in math, for example, multiplying by 0 is idempotent. So no matter how many times you do it, you're gonna get the same result after the first application. Whereas if you look at HTTP, GET requests, PUT requests, and delete are all idempotent. But notably, POST is not, right? So if you submit the same POST request twice, you're actually going to create 2 resources. And as I mentioned, our automations can mutate state in external systems, such as EHRs. And our workflows can fail midway due to issues outside of our control, like maybe the customer VPN goes down. And when the workflow retries, we don't want to repeat mutations that we've already done. So we need idempotent APIs to give us what's called at most once semantics, which is basically a guarantee that we will only do the work at most one time. We're not going to duplicate the work if we only intended to do it once. And AWS published this really excellent blog post called Making Retries Safe with Idempotent APIs. I recommend you read it. I'll try to give you a very brief summary of it. And they talk about having the same problem internally. So the blog post talks about the example they use is creating an EC2 instance. So to the client, creating an EC2 instance seems simple. But internally at AWS, it actually requires several API calls, each of which has some chance of failure associated with it. For example, they have to pull together a network interface, an EBS volume, a VM, and each of these API calls internally can fail. And their question is, how do we make sure that we end up with exactly one EC2 instance at the end? And specifically, let's say the client submits the request and the request times out. So the client doesn't know what happened. So they're just going to submit it again. But they probably don't want a second EC2 instance. They probably want, they're probably just following up on their initial request and trying to figure out what happened. And so AWS's question is, how does AWS figure out if a retry that's coming in is actually a retry of a previous request, or if it's a unique request now? So the first idea they have is that on the server side, they can hash all the parameters that are coming into the function call and dedupe requests that way. So for example, if they see a function call that has all the same parameters as a very recent function call within some time window, then they decide that it's a duplicate, and they coalesce it and only do the work once and give you back one EC2 instance. But this is kind of weird, because sometimes you may actually want 2 identical EC2 instances around the same time, and that's a totally valid option. And the other option that they talk about is that the client basically generates a unique token and adds that to its request. And the client can retry as many times as it wants, but it's always passing in this token that doesn't change. And so if it's a retry, the client passes in the same token. But then if the client says, actually, I want a second EC2 instance, it makes a new token and submits a request again. So basically, the client is controlling the semantics here. And this is what AWS actually uses. I think this is a very powerful concept. You may be wondering, you've never had to generate a token when making an EC2 instance, and that's because the SDK handles all of this for you. But this concept is really powerful, because it allows the client to distinguish between basically what's a retry of a previous request and what is a new request that you want new work to be done for. And idempotent APIs are interesting because they lead to this idea of replayable workflows. So to Casa, all of our internal APIs follow the client token pattern, which means if the client resubmits the same request with the same client token within a reasonable window of time, the response is immediately returned from the server's cache. Like the server doesn't even try to do the work again. This is at most once semantics. We're only going to do the work once. And so then if you imagine this case I've been talking about, a workflow fails midway through a series of API calls. What we can do now is we can simply restart it from the very beginning and just fire off all of the API calls again, starting from the first one. And if the call had already been made, then the server is going to recognize that, hey, I've seen this client token before, and it's just going to instantly return the response from the cache. And then once you get to the part that failed, where you never got to submit the sixth API call in the workflow, the server doesn't see any cached result, and so it starts doing the work. And this pattern creates what we call replayable workflows that allow you to basically replay everything from the beginning, and you don't have to worry about saving intermediate state or remembering where you left off, which makes the code very simple to write. OK, so quick time check. OK, I will now try to summarize how we built a workflow engine on top of the idea of replayable workflows. And I'm going to go a little bit fast, just for time, but happy to stay afterwards for questions. OK, the first thing that's important to understand, I'm going to walk you through basically slide by slide what the architecture looks like. So an engineer writes these functions or these building blocks that I talked about to do things like scrape an EHR or perform data entry or run an ML algorithm or so on. And they decorate each function with our workflow.task decorator. And there's a single Python script where they sort of tie together all the functions, calling them in the right order, taking the output of one API call and passing it as the input to the next one, and so on. And this script looks super simple, and you write the script as if it's executing in a completely synchronous manner. But what this decorator is doing is that as the script executes, rather than invoking the functions directly, the decorator is actually pushing the functions onto a queue. And then it immediately raises a pending exception to say that, hey, this function is still pending. So you can exit now and come back and check it later. So the takeaway here is the engineer writes a single Python script that looks super simple. It looks like it's synchronous. You can do for loops. You can do conditionals. You can do whatever you want. But instead of actually running these building blocks, these API calls directly, we're pushing them onto a queue where they will be run asynchronously. And we don't block while waiting for these things to run, because again, sometimes they can take several minutes. So we exit and the process can do something else. Now on the other side of the queue, we have the workers. So we have a pool of workers that's running. And the worker is dequeuing tasks from the queue and then actually executing the function. And when the worker finishes executing the function, it's going to write its results to the database. By the way, and mark the tasks as done. So in healthcare, we typically don't have massive data. And additionally, due to data privacy regulations, we have to shard all our databases by customer anyways. And that means that right now using the database, basically Postgres as a results store, has worked perfectly fine for our workflow engine. Though if we ever scale to much bigger data sets, that we would probably swap this out. But right now we use basically Postgres-based queue. And so we're using Postgres both as the queue and as the results store. And we used an open source library and did a couple of cool things on top of it, like adding this results table to store status and results of each task, so you don't get this fire and forget model where you submitted a task to the queue, but you have no idea what happened to it. We also added a REST API on top of the queuing library so that you can enqueue tasks from non-Python code. You can enqueue it from a bash script or whatever. But the main takeaway on this slide is workers are pulling tasks off of the queue and executing them according to task level priorities that we're setting. So what we've talked about so far is you write a script. As the script executes, it doesn't actually do the work, but it pushes the work onto a queue. Then you have workers that are grabbing the work off of that queue and doing the work and writing their results to a database. So then at some point, the original script needs to get the results and kind of keep pushing the workflow forward as the results are being done. So as I said, the workflow gets the special exception class we created called a pending exception immediately when it first submits a function call. And then the workflow retries periodically to see if the work is done. But what's important is that there's no status endpoint here. So the workflow is not remembering what call it submitted last and calling the status endpoint for that API. Instead, it's doing this replay idea that I told you about, where the workflow just restarts from the very beginning, and fires off the same chain of requests with the same client tokens. And so again, the worker checks the cache. The worker checks the cache, and if it's already seen a client token, it doesn't do the work again, and it just returns the results from the cache. Or if the results are still pending, then it raises pending exception again to tell you that the task is still in progress. So this is how this idea of replay becomes real, which is that the workflow keeps retrying. It starts from the beginning. Let's say previously it had gotten through 5 out of 10 API calls. These first 5 are going to be instant on the replay because you basically submit the function call, immediately get the cached result back, submit the next function call, immediately get the cached result back, and so on. And if we wanted even lower latency than this idea of polling, we also implemented notification, which means that when a worker completes a task, it knows who's waiting on it, and it can basically call a callback to go notify that dependent task. So the takeaway on this slide is that the workflow can just retry the exact same code. It doesn't have any special code for statusing or anything like that. And work doesn't get duplicated based on the client token semantics. OK, so I told you we're pushing work onto a queue, right? So we need a consistent way to serialize and deserialize task inputs and outputs. And so the way we do that is that all function inputs and all return values are Pydantic models. And when we are pushing work onto the queue, the arguments get serialized, and we write them into the database. And then when the worker is picking up work off of the queue, it's deserializing the arguments from the database. So now it has the arguments that it needs to run the function with. And then when it finishes, it takes the return value and serializes those and writes it back to the database. So basically, all I'm saying here is that we need a consistent way to pass inputs and outputs around and make sure we don't lose anything in translation because we have this intermediate layer of the queue. We just need to make sure that we are serializing and deserializing everything correctly. And that's what we're using Pydantic for. And then the last part, which obviously is pretty important because it's kind of how all the magic works, is about how we generate client tokens. OK, it looks like I still have a few minutes. OK, so the framework, I'll say a statement, and then I'll try to explain what that means. The workflow engine framework automatically generates client tokens in a way that takes into account what we call the call stack provenance. So what I mean when I say call stack provenance is it takes into account, everything that's happened up above it in the call stack. And if something there has changed, like if some parent node or ancestor node changed, then we automatically invalidate all descendants and recompute them. But if everything in the ancestry is the same, here actually, then let's talk about this. Okay, so you can imagine a Python script being represented as basically a call graph, where you have like some root node, like a main method, and then any other node has a parent, right? Because you have functions that are calling other functions. For the root node, we calculate the client token by generating a hash of the arguments to the main method, or whatever the method is that initializes the program. But then any other function call, like let's say function x, is always going to be invoked by some parent function y. Okay, and so how we generate the client token for function x is the client token is a hash of all the arguments to x, but it also hashes, it also includes in the hash function the client token of its parent function y. And so this gets us the desired behavior. I'm going to try to go slow here or repeat this because this is important. So if the arguments to the child task, in this case, that child task is function x, if the arguments to function x change, then we get a new client token because what we're hashing is going to change. Like we have a different argument in here. We get a new client token and we do the work again. And that's usually what we want, because we don't want to be returning a result from a cache if we're now passing in different arguments. So that's totally reasonable to redo the work if we change the arguments to the function. But additionally, if any arguments change anywhere up in the call stack, like in the ancestry, then what's going to happen, by the same logic, is that parent function is going to get a new client token. And since the parent function client token is included when you're creating the child client token, you basically invalidate all of the descendants and recompute. And so I know this is a little complicated. Happy to take questions about it later. But the key ideas here are that we can replay everything, and as long as no arguments change, we get replay behavior for free. We instantly get results back from the cache. But if any arguments change and you want to invalidate results, that behavior also comes for free. And our framework includes a decorator that automatically generates client tokens in this manner so that the engineer doesn't have to think about it. Okay, I think this is my last slide, or one of my last slides. So putting it all together, just trying to sum up the experience here. An engineer is writing a Python script. The code looks super simple, and it looks like it's synchronous code. But during execution, tasks are actually pushed onto a queue rather than executed in process. On the other end of the queue, you have workers that are polling the queue and working tasks in order of priority. And the workflow script is continuously retrying. And as it gets results back, it's firing off the next API call, basically queuing up the next task. And no duplicate work is done since client tokens are generated in a deterministic manner. And the workflow code looks really simple. And if we are waiting on a high latency task, like let's say we are now asking a human to go label some data and it's in the middle of the night, so we may not get a human to help us for a couple hours, we're not blocking and waiting for a human during that time. We submitted an API call, but we get the control of the process back, and the workers are free to go pick up other tasks during that time that can be worked in parallel. For example, scraping more websites or scraping more data from the EHR. Eventually, when the human wakes up in the morning and gets to this task, then we'll no longer get a pending exception the next time we go to poll it, and we can kind of move that workflow forward. But while we're waiting for them, our workers can go do other things and aren't being consumed with that. Okay, so I think that's all I got. I had some screenshots here just to show that we also built a nice front end on top of it, and that allows you to kind of see how everything is working, allows you to debug and see all the inputs and outputs, the stack trace if a function has an error, and so on. Let's see. Probably don't have time for much of a demo.
We're running a little bit late.
Okay.
So, let's thank our speaker. Are there any questions? We have a few questions. Also, we're at 12:30, so if you want to head out, feel free. We're not stopping you, but we can also stick around for Q&A.
Yeah, I was wondering if you looked at existing orchestrators that are out there and what you found deficient or led you to build your own.
Yeah, for sure. We looked at a bunch, actually. I have another talk that I sometimes give on the sort of the audit that we did. There were a few categories. A lot of workflow engines out there were built around this idea of, you write a DAG, and then they go execute that DAG very efficiently for you. And that didn't work for us because a lot of our workflows, as I mentioned, are super dynamic and are actually just difficult to express as DAGs. That was one area. There were other tools like Cadence and Temporal and Prefect that looked pretty interesting to us. And I think maybe timing was a little bit wrong. So we're a Python shop, and I think the temporal Python support was not great, at least at the time when we were needing a solution. Prefect, if you haven't looked at it, looks quite interesting, and Prefect v2 looks fairly similar to what we ended up building, but it didn't exist when we built this. So yeah, that's kind of the short summary, but happy to go into a lot more detail.
Hey, great talk. I had a question about how do you actually maintain the order of operations if you actually have a DAG? So you're doing like asynchronous work, and then you have this workflow, like task A or function A, B, C, they need to go in order, right? And they're queued up. And you're actually doing task A, B, C asynchronously of each other, or is task B or C waiting for B and then B waiting for the output of A?
Yeah, good question. Yeah, so certainly when you have sequential tasks like that, so you'll queue up A first, you'll get a pending exception, the workflow will stop right there. You haven't even queued up B yet. Once you get the results of A back, this is assuming assuming you want this linear flow where B requires A's output and C requires B's output and so on. Yeah, so you only queue them up one at a time. And once you go to poll and you don't get a pending exception, then you queue the next one up. So that's basically supported by default if you want that sort of linear execution. We also do support syntax for in parallel creating, a bunch of tasks at once if you do want them to run in parallel.
Got it. And thank you. And all of this, are any of your tools open source? I didn't catch that. Can we install them or no?
Not right now, but that's something we're hoping to do either probably early next year is our hope. We would really love to make this open source.
Great. Thank you.
Mm-hmm.
All right. Thanks a lot. Sanjay, sorry for the technical difficulties. One more question. Okay.
Hi, great talk. Thank you so much. I just wanted to know how this integrates with EMRs like Epic matters and who are your most important customers. Thank you.
Yeah, absolutely. We work with some of the biggest health systems in the world, though I don't think I'm at the liberty to disclose all of their names. You can look on our website, acasa.com, for the ones that are publicly disclosed. But yeah, some of the biggest hospital systems in the world are our customers. We integrate with all the different EMRs, Epic, Cerner, and so on. And basically how this works is, what I talked about is we can build a robot to basically act like a human and control the desktop. And then from there, we can program the robot to do different things based on what the equivalent human person would be doing. So maybe in one case, it is, submitting appeals based on denials that were incorrect. In another case, it might be checking the status of claims and flagging them in the system if they need to be worked on. So basically, that's kind of our whole business is offering like a virtual full-time employee and just making it so that a robot can do all the same stuff as a human, but obviously way faster and way more productive.
That's the one final question.
Hi. Thanks for the talk. I just really appreciate everything you've talked about today. My question is about, so in the seminar description, you mentioned FastAPI, and I was just wondering if that was, like, if you guys actually use that as part of your toolkit, and if so, how did you come to that decision?
Yeah, we do. And sorry, I totally forgot to cover that. One thing that's super cool is basically anything you tag as a workflow task using our decorator automatically gets exposed as a FastAPI endpoint. So that's another part of what our decorator does. And so that means that you can queue up these tasks, again, like from a bash script or from another programming language just by hitting the FastAPI endpoint. So that's what we're using FastAPI for, is basically as a REST API on top of the queue, and making it so that if you are another service within the company, you don't have to know that we use queuing or any of that. Like, that's an internal detail that you shouldn't care about. You just submit an API request to call the endpoint that you want, and then what we're going to do on our end is push that function onto a queue and have a worker go work on it. Does that make sense?
Yeah, thank you.
Mm-hmm.
Okay. Cool, awesome. Well, thanks again, and it's lunchtime. All right. Thanks, Sanjay.
Alrighty, thanks so much. I apologize for the technical difficulties.
Oh no, it's our fault.
Nah.
Bye-bye.
Okay, bye.